Okay, in this video, we're going to continue our study of transformations of functions and look at two different types of transformations that will involve stretching and shrinking graphs and also reflecting graphs. So the first part of this lesson will be on vertically stretching and shrinking graphs, and we will be comparing the graphs of y is equal to a times f of x to the graph of y is equal to f of x. So a is just a number that we are multiplying by a function, and there are two cases to consider: when a is greater than 1 or when a is between 0 and 1. Now I could do this on Desmos for you to see it pretty quickly what the result is, but let's just do this manually. So if I want to look at the graph of y is equal to x squared and then compare it to g of x, which is equal to 2 times f of x, understand that 2 times f of x is nothing more than 2 times that original function, which is x squared. So we want to observe how 2 times x squared relates to the graph of just y equals x squared. Well, 2 times x squared, we can plug in the values for x, like -2, -1, 0, 1, and 2. Be careful with the order of operations when you do this. If we plug in -2, we would have 2 times -2 squared. Order of operations is we have to square first, so that's 2 times 4, which is equal to 8. Substituting -1, we get 2 times -1 squared, which is 2 times +1, or 2. Substituting 0, 2 times 0 squared is just 2 times 0, or 0. Substituting 1, 2 times 1 squared is 2 times 1, which is 2. And lastly, we substitute 2 in for x to get 2 times 2 squared, which is 2 times 4, or 8. So notice we have the order pairs -2, 8, -1, 2, 0, 0, 1, 2, and 2, 8. So I have already on my graph the graph of y is equal to x squared. And remember, that's one of those basic functions I said you need to know the graph of. This is a parabola that goes through the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And so now I'm going to plot the points for the new function on top of this. -2, 8 is a little bit off my screen. -1, 2, 0, 0, 1, 2, and then 2, 8. And so notice that I get a parabola when I connect these points. Now this is one of those non-rigid transformations because we are actually changing the shape of the parabola, right? It's not the same width. We are actually making it skinnier when we multiply it by 2. And think about this. If you've ever pasted an image into a document and you grab the corners and you pull it up, right? You're making it skinnier. It stretches it up. And that's exactly what this multiplier of 2 is doing to this graph of y is equal to x squared. So when we state how it relates, we say that the graph of g is the graph of f stretched by a factor of 2. Now notice also what changes here. The x values stayed the same, but the y values were multiplied by 2. In fact, that's what we're doing. 2 times f of x is really nothing more than 2 times y. So we're changing the y values by a multiple of 2, which gives the effect of stretching the graph. Now we want to look at the graph of g of x, which is equal to 1/2 f of x. Again, f of x is x squared, so this is equivalent to 1/2 times x squared. So I have a table of values, and I want to plug in -2, -1, 0, 1, and 2. When I replace x with -2, I get 1/2 times -2 squared. And remember again, the order of operations, we square first to get 1/2 times 4, which is 2. 1/2 times -1 squared is 1/2 times 1, or 1/2. 1/2 times 0 squared is 1/2 times 0, or 0. 1/2 times 1 squared is 1/2 times 1, or 1/2. And then 1/2 times 2 squared is 1/2 times 4, or 2. So we have the order pairs -2, 2, -1, 1/2, 0, 0, 1, 1/2, and 2, 2. So again, on my coordinate system, I have the graph of y is equal to x squared through those points, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. When I plot the transformed points, I have -2, 2, -1, 1/2, 0, 0, 1, 1/2, and 2, 2. So here again, we have a parabola, but notice that the parabola now is kind of on the outside of that original graph, right? Our parabola now is wider or fatter than the original parabola. And so this is the equivalent of vertically shrinking or compressing the graph. Think about standing on top of the ends of that parabola and pushing it down by a factor of 1/2, and that's what you would get. So we say that the graph of G is the graph of F vertically shrunk or compressed by a factor of 1/2. And I guess to be precise on my previous one, I should have said the graph of G is a graph of F vertically stretched. There are horizontal stretches that can be used to transform graphs. We're not going to study that in our particular course, but we are talking only about vertical stretching. And those, again, are the changes to y, right? The x values remain the same, but the y values were cut in half. And that result is a compression to the graph. So we'll just summarize these two effects in a property. Property 3 is for vertical stretches and shrinks. So when a is a positive real number greater than 1, the graph of y equals a times f of x is a graph of f vertically stretched by a factor of a. And so if the point xy is on the graph of f, then the point x a times y is on the graph of y is equal to a times f of x, right? We just talked about that in like the graph of y equals 2x squared. 2, 4 was on the original graph, but 2, 8, which is really 2 times 4, right, is on the graph of the transformed graph. Then part B of that property is when we have a positive real number that's between 0 and 1. The graph of y is equal to a times f of x is a graph of f vertically shrunk or compressed by a factor of a. So if the point xy is on the graph of f, then the point x a times y is on the graph of y equals a times f of x. The next type of transformation we want to discuss is reflections. So think about the word reflection just in everyday life. If you think about a pond and you see the trees reflecting in the pond, or you look in a mirror and you see a reflection of yourself, you're basically seeing a mirror image of yourself, right? So this is what we're going to talk about with the graphs. We're going to look at how we can reflect graphs across either the x-axis or y-axis. And these again are rigid transformations because the shape of the graph is still the same. So we can look at f of x is equal to the square root of x, and we want to graph the function g of x, which is equal to negative f of x, and state how its graph relates to the graph of f. So f of x, the square root of x, is just this half parabola that goes through 0, 0, 1, 1, 2, 1.4, and 4, 2. So now we want to look at g of x, which is equal to the opposite of f of x, but this is really just the opposite of the square root of x. So the domain is not changed here. That is, the domain of the square root of x is x has to be greater than or equal to 0, and that's the same thing for this particular function g. We're not changing the inside part, we're only changing the outside. So there's a change to the y value in this graph. So I can plug in values for x, which are exactly what were in my original function. So we will plug in 0, 1, 2, and 4 and see the transformation that takes place. So g of 0 is going to be the opposite of the square root of 0, which is the opposite of 0, which is just 0. G of 1 is the opposite of the square root of 1, which is just negative 1. G of 2 is the opposite of the square root of 2, which will be approximately negative 1.4. And then g of 4 is the opposite of the square root of 4, which is negative 2. So I have the ordered pairs 0, 0, 1, negative 1, 2, negative 1.4, and 4, negative 2. So whenever I plot these on this same graph, we'll see the result. So 0, 0, the origin, 1, negative 1 is in quadrant 4, 2, negative 1.4, and then 4, negative 2. So notice that I still get a half parabola, but it's kind of an inversion of the original graph. In fact, if I folded the graph across the x-axis, I would see its mirror image. And so we say that the graph of G is the graph of F reflected across or over across the x-axis. And the way I think about this is that we're taking the opposite of y, right? And the opposite of y, if we think about the y-axis, above the x-axis and below the x-axis are where we see the opposite values for y. And so to see the opposite of y, we have to reflect across this x-axis. And now we want to examine the graph of g of x, which is equal to f of negative x. So here we have an interchange. And so my function for g is written as a square root of negative x, right? We just replace the x in the original function with negative x. Now because we have a change on the inside, the domain is impacted. We have to make sure that negative x is greater than or equal to 0. But when we divide by negative 1, x is less than or equal to 0. Remember, the division by negative changes the inequality sign. So I have to plug in values that are 0 or less, right? So negative values and 0. So g of 0 would be the square root of the opposite of 0, which is just the square root of 0 or 0. When we plug in negative 1, we would have the square root of the opposite from the function, and then the number we're plugging in is a negative 1. So this becomes really the square root of 1 or 1. When we plug in negative 2, we get the square root of the opposite of negative 2, which is the square root of 2 or approximately 1.4. And then when we plug in negative 4, we get the square root of the opposite of negative 4 or the square root of 4, which is 2. So we have the ordered pair 0, 0, negative 1, 1, negative 2, 1.4, and negative 4, 2. So we want to plot the solutions to this function g on top of the graph of f. So again, y equals the square root of x, goes through these points 0, 0, 1, 1, 2, 1.4, and 4, 2. So we're going to plot the new points 0, 0, negative 1, 1, which is in quadrant 2, negative 2, 1.4, and then negative 4, 2. So this time we have a parabola, a half parabola, that opens to the left. And notice how it relates to that original graph. If we reflect it or do the mirror image across the y-axis, we get the exact same graph. And so we say that the graph of g is the graph of f reflected across the y-axis. And so again, the way I think about it is, in this particular transformation, I'm taking the opposite of x. Well, where do I find opposite of x? To the right and left of the y-axis, right? So to obtain this graph, I have to reflect the original function across the y-axis. And notice that the x values are opposite of what the original points were. So in this case, the y value stayed the same, but the x values are opposite. And so we can sum this up. So property 4 on reflections is if we have y is equal to f of x, the graph of y equals negative f of x is a graph of f reflected across the x-axis. So it's important to know that if xy is on the graph of f, then the point x negative y is on the graph of y equals negative f of x. That transformation only impacted the y values because it was an outside change. And the second part of this is the graph of y is equal to f of negative x is a graph of f reflected across the y-axis. So if the point xy is on the graph of f, then the point negative x, y is on the graph of y equals f of negative x. So here the inside change impacted the x values, but the y values stayed the same.